Hello everyone, welcome to webinar on dynamic analysis with MIDAS Gen. My name is Nivedita Khole. I'm a technical support engineer in MIDAS IT. Without any further delay, let us begin with our webinar. MIDAS Gen, as you can see, it's written as one-stop solution for buildings and general structures. Why one-stop? Because you can have the analysis and design of steel as well as concrete, superstructure as well as substructure in the same model and analyzed at the same time. So that makes MIDAS Gen a very dynamic software solution. Let's look at its applications now. These are just few applications in front of you so that you can maybe understand how dynamic the software is, vast the software is. Well, when it comes to buildings, there is Burj Khalifa, which used MIDAS Gen program for column shortening analysis. That was the only reason why they issued it, because they had previously used another software for their primary analysis and design. Other than that, there is Moscow City Palace Tower, Gate of Orient, and Gangs of Twin Tower, which have completely used MIDAS Gen as a primary software for analysis and design. Not just buildings, but spatial structures, which include RC as well as steel in it. So we can see Beijing Stadium, Beijing Gymnasium, Jeonju World Cup Stadium, Incheon International Airport. So spatial structures can also be easily modeled, analyzed, and designed in MIDAS Gen program. Next, coming to specialty structures, you can see that over here it's not just frame elements, but also you can analyze the shell elements and solid elements. So MIDAS Gen is not only constrained to frames, but also shell modeling can be done, analysis and design can be done, and solid analysis can also be performed. So these are few applications of MIDAS Gen program to showcase to you today. Now let's go ahead and look at MIDAS Gen's major strengths. The major strengths of MIDAS structural solutions are displayed right over here. These are actually listed down by our clients. So you can totally rely on this. If you would like to ask anyone, you can definitely out of our users, which you must have definitely got when we had sent you invitations. Okay, so let me just go through all these major strengths very quickly. Starting with the works tree, it becomes a user-friendly tool because at one glance you can look at it and understand what all things have been incorporated in the model. Then meshing of planar and solid elements is so efficient in MIDAS Gen program. You do not have to worry about the mesh size. You do not have to worry about the shape of the mesh. You don't have to worry about the nodal connectivity. All is taken care of by the program, making the structure accurate and also saving your time. Then we have automatic story diagrams. In other programs, you have to basically select the floor or select the nodes, and then you need to attach the diagrams, that is rigid diagrams or semi-rigid diagrams. However, in MIDAS Gen, by just defining the stories, we can simply get the diagrams detected and applied by the program. So it's a time-saving feature. Coming to the soil structure interaction, well, IS 1893 has actually mentioned about soil structure interaction, making the structure cost-effective. This is available in MIDAS Gen program. We will be having our next webinar session on soil structure interaction. So if you're interested, you can definitely join in for the next session as well, which is actually going to be on 29th. Okay, so next is automatic wind loads. Well, in few softwares you have to calculate the wind loads and apply on the structure using element loads or nodal loads. However, in MIDAS Gen, we can apply the loads by simply specifying the parameters, and that's it. So that makes it time-saving and accurate. Then there is auto excitation angle for response spectrum. Well, I'll be explaining this because we will be performing response spectrum. It's a linear dynamic analysis, that's why. It's a time-saving feature, and when it comes to highly seismic regions, we need this excitation angle to make the structural analysis pretty accurate. Then further load loadings, you do not need to create slab elements. You can use float loads in any plane, very easy and time saving. Then further we can apply hydrostatic pressure, which is again a time saving feature for water tanks like that. Then there is increase in the speed of analysis because of the multiple cores that you can use, and also we have GPU accelerator that can help with increasing the speed of the time of the analysis. So basically the analysis speed is dependent on your hardware and not the software. Alright, then further we have advanced analysis, that is column shortening, moving loads, heat of hydration, masonry, pushover analysis, inelastic time history analysis, which we will be also discussing a little further during the demonstration. Then when it comes to results, that time we need to look at certain irregularities in a structure. So those irregularities are automatically detected by the program, and we are getting those results by story tables. So it makes a time-saving feature. You do not have to do any modifications, taking the results into Excel sheets and then checking with the codes. No need to do that. So we will see this as well. Then further, dynamic report generation, which is a time-saving feature in MIDAS Gen. Last webinar we had seen this. Then further, there is detailed design reports that can be generated by the program. It is like pretty clear because it is arranged as per the coded provisions. So you can see that. Then we have optimal design for RC members, as in you can modify the RC section properties during the design period and see if that section is passing or failing. You can have a preliminary sizing done at that point, and then further you can reperform the analysis and design. So that's about the optimal design. Then the design methodology is similar to the coded ones, so you can get an accurate design. And further we have MIDAS Design Plus, which is the independent component designs tool. It's pretty handy, so in case you're like just want to check, you just have got the reactions and you just want to check the design of the footings, then you can simply use MIDAS Design Plus for that. Then further, rebar detailing and quantity estimates. This is done in MIDAS D Shop, that is a drawing shop software solution. You can generate drawings and bill of materials very quickly, saving a huge time. So these are few major strengths that I just mentioned right now. Now let's go ahead for the demonstration in MIDAS Gen program. Alright, so today our topic is basically dynamic analysis. It's of course more related to the seismic analysis procedures. So let me just take you quickly through what all procedures are there when it comes to seismic analysis. Well, we can perform linear as well as non-linear, static as well as dynamic analysis in MIDAS Gen. All these listed analysis can be performed in MIDAS Gen program. We have seen in the last webinar how equivalent static seismic load can be applied on the structure. Also, response spectrum analysis was seen. However, today we will be focusing on the dynamics, so we will be repeating this part. We can perform pushover analysis, which is a nonlinear static analysis. And also, when it comes to nonlinear dynamic analysis, we do have an elastic time history analysis. As per IS 1893-2016 clause 6.4.3, we can perform the dynamic analysis in three ways. One is response spectrum method, second is modal time history method, and the third is the time history method. You can say inelastic one. So we can perform all of these three in MIDAS Gen program. We are going to be looking at response spectrum analysis and inelastic time history analysis as a linear and non-linear dynamic analysis in MIDAS Gen program. And as per IS 1893-2016 clause 7.7.1, we need to perform this dynamic analysis if our building is irregular and it is of height greater than 15 meters if it's in seismic zone 2. Otherwise, in other zones, we need to perform dynamic analysis. And also, we need to check if the approximate natural period is greater than 0.4 seconds. If it is greater than 0.4 seconds, we need to perform the dynamic analysis. Alright, so that's what we're going to be doing. So firstly, we are going to be looking at the modal response spectrum analysis procedure in MIDAS GEN program. Okay, so this is MIDAS GEN software solution. Let me quickly take you through the user interface of the program. So just in case anybody who is new to MIDAS GEN webinar sessions, then you will understand again. Okay. So here we have at the top ribbon menu, which is divided into different tabs. These are the tabs, and all these tabs are arranged as per the work procedure from left to right. So first 4 tabs are for modeling, then you go towards the right side to apply the support in the boundary tab, then you apply the loads, then you perform the analysis, then you check the analysis results, and then you can go ahead for the pushover, or you can go ahead for the designing. In the query, you can get summary tables, node detail tables of your structure, and in the tools tab, you can generate dynamic reports. Then further, we have tree menu over here on the left side. We can have it on the right side as well. However, all the commands open up in the left tree menu. The important part in the tree menu is the works tree menu, which was one of the major strengths in MIDAS GEN. Unlike any other program, this works tree menu actually shows us the only information that is related to the structure, nothing extra. Alright, so we have 6 stories and we have trusses and line elements, which are called as beams in MIDAS GEN. Then we can see here the material property used is E250 as per Indian standard. The sections used are these, and you can just simply double click and understand which of these section properties are assigned to which elements. You can even do the modification of the properties by simply drag and drop features that we have in MIDAS GEN. So it's simply like I select an element and I simply drag and drop to change the property. So it's very easy, intuitive. Alright, next, if I go down, we can see the boundaries that have been applied, which include supports. We can see over here, this designates that it's a pinned support. We can even right click and say display to see that these supports have been applied to the lowermost nodes of the structure. Next, we can see over here the loads that have been applied, static loads especially. So we can see that under the dead loads, we have the self-weight applied. Then the flow loads have also been applied on the structure, the one-way flow loading. And further, as live loads, again flow load has been applied. We have applied over here static seismic load in the X direction, and there is static seismic load applied in the Y direction. So this is the works tree menu explaining only about the model that we have over here. Next, at the bottom you can see we are having a unit system, which is kilonewton meter, and we can go through any views by clicking on these quick viewing tools. Alright, so here is our user interface. Now let's go ahead and see how to apply the response spectrum loading. One important part in applying seismic load is that we need to go through a few things, preliminary things. One is the mass. We need to define the mass. We have applied the loads, but the mass is not there. So we need to go ahead and apply the mass to the structure. So that can be done in MIDAS GEN using 2 functions. One is under the structure tab, structure type. wherein we check on the convert sulfate into masses. And depending on the application direction of the seismic loads, we can use these commands. Alright, so this is done. And the next part is under the loads tab. We have loads to masses. Under the loads to masses, we need to convert 100% of the dead loads, and you can convert 25 to 50% of the live loads. So I'm using 25% here and add. So this is done. Alright. Now, as per clause 7.7.5, firstly we need to define the spectrum. So the spectrum that you can see in the figure 2b can be generated automatically by the program. So let us see that. After we are done with the loads to masses function, we will go to the dynamic loads type. Alright, so into the dynamic loads, firstly we can see here that there is a section for response spectrum data. And application of response spectrum is very easy. It's just two tools that we need to use. First is to define the response spectrum function, and the second is the response spectrum load case. So let us start with defining automatic response spectrum definition. So all you need to do is click on add, and we can click on the design spectrum over here, and then you can simply go ahead and select the Indian standard. Now I have always been mentioning it's IS 1893-2016. This is because MIDAS Gen has an advantage over other softwares, and that is updating codes. MIDAS Gen always takes care that all the codes, the latest codes, have been incorporated in the software so that you do not miss out on anything and completely work on the software without any problems. Alright, so there is IS 1893-2016, which we're going to be using. We'll use seismic zone 2, soil type rock and hard soil, keeping all the parameters default. Damping percentage will be 5% itself. Our structure is a steel structure. However, in the latest standard, the damping percentage is no more 2% but 5% itself. Alright, so we have 5% of damping, and response reduction factor for an OMRF steel building is 3 itself, so I'm keeping as that. And maximum period I'm keeping as 6 seconds. So there we go. We get a graph, and it's a normalized acceleration graph. This is also an advantage wherein you do not have to divide the graph values by the gravity because it's already done by the program. Alright, so that's there. Damping ratio is there, and all you need to do is simply click on OK. We're done. Just simply defining the parameters, we click on OK, and we're done with the spectrum definition. Now we'll close and go ahead for the next step, that is response spectrum load cases. In the response spectrum load case, the command opens up on our left tree menu. We need to simply provide over here the response spectrum load case name. Now, actually, response spectrum loading is based on the is like a superposition method based on the eigenvalues. So what we need to actually know over here is the maximum base shear. Now, when it comes to a regular floor plan as this, it's a symmetrical floor plan as you can see over here. At that time, application of this response spectrum loading in the X direction and Y direction is okay. One of the directions will be our major angle, and we do not have to worry further. However, when it comes to an irregular plan, at that time, Indian standard specifies Indian standard specifies that you need to use 130 rule. That means you need to apply 100% in the X direction and at the same time 30% in the Y direction. Alright, so but that approach basically is a little inaccurate, conservative, approximate, and that's why it's not much recommended in highly seismic regions. So MIDAS Gen offers you the auto search angle option. Auto search angle option is the one which can automatically find out the major angle of the response spectrum loading, because of which you will get maximum base shear, and that makes the analysis very accurate. Alright, so we are going to be using this auto search angle and checking out which of the directions is our major and minor angles. Alright, so I'll just name it as RS major, since I've used major over here. And then further we can see over here the modal combination control. So in MIDAS Gen we have the CQC method, so no worries, but we do have alternate methods as well, like the SRSS and absolute method mentioned by the code. One advantage that we have in MIDAS Gen program is the add signs to the results. Alright, because we usually get absolute results because of the CQC method of combination, and the results could be a little bit critical or not correct if we miss out the sign. So MIDAS Gen has the possibility to apply the positive negative signs to the results, and that can be decided based on these two options available, like along the major mode direction or along the absolute maximum value. So I'm keeping on along the major mode direction. Further, we do not have mode shapes for now because we have not performed the analysis yet, and so I'm unchecking this box and clicking on OK. So that's the modal combination control. Then we go ahead to check on the spectrum function that is going to be used for that load case. Alright, then further we do have options of applying damping method. So in case you have applied different dampings for different elements, then you can use different damping method. And if you have multiple spectrum functions, then you can do interpolation of the spectral data as well. We have two options, linear interpolation, logarithmic interpolation, and we recommend logarithmic. Alright, and next is the accidental eccentricity. So accidental eccentricity can be applied to dynamic seismic loads by specifying over here the eccentricity, which is automatically taken as 5% of land dimensions as per the standard. Alright, so that's the thing, and then further we are going to just simply click on add. Alright, so the procedure was simple, just had to provide a name. Now I'll create another one, which is the orthogonal direction. Alright, so just provide a name and the angle and check on the function, and then simply you can even check or uncheck the accidental eccentricities and then click on add. So I've not used the accidental eccentricity for my statics, so I'm just unchecking and modifying this. Alright, so we are done with the load case definition and we are almost done. The last part is the eigenvalue analysis control. So let me take you to the presentation again. Last time we have gone through the Know Your Codes webinar. So that's the same slides I've taken down over here for a quick reference. So it's important for us to understand that as per the Indian standard, clause 7.7.5.2, we need to consider the number of modes so that we get at least 90% of mass participation. And this can be done or checked with the help of eigenvalue analysis. So let's go back to MIDAS Gen and see what all things are available. So when it comes to eigenvalue analysis, we have two types of analysis. One is eigenvectors and the second one is Ritz vectors. Alright, so eigenvectors is the most accurate type of analysis. Ritz vectors is approximate. This is because eigenvectors take care of all the masses in your structure, whereas Ritz vectors takes care of only heavy masses of the structures first. So basically If you have a simple structure, you can go ahead with the eigenvectors, wherein you'll get the 90% of mass participation by using 100 to 200 mode shapes. If you're not getting the results or 90% mass participation in about 200 mode shapes, then you can definitely go ahead for the Ritz vectors. Alright, when it comes to eigenvectors, again we have subspace iteration and Lanczos iteration. This Lanczos iteration is a very accurate solution as well, analysis as well, and however it works only for 30 number of mode shapes. Now since our structure over here is just 6 stories, it's somewhat 19 meters of height, I do not need frequencies more than 15, so I'm just going to provide 15 number of frequencies, which is nothing but 15 number of mode shapes. Alright, so we are done with specifying the eigenvalue analysis. Alright, now in dynamic analysis, it's very important for us to go for the eigenvalue analysis, be it for response spectrum or be it for time history, because we are going to be needing the modes. Alright, so we are done with the response spectrum procedure. All we need to do now is go ahead in the analysis tab, which is the next tab, and perform the analysis. Alright, analysis has been performed. We can see that it just took 0.58 seconds to perform the analysis of a 6-storied steel structure along with dynamic analysis. This is because the software has a 64-bit solver speed, and with GPU accelerators you can increase the speed further. My system is i7 with NVIDIA GeForce graphics card, so it took like 0.58 seconds. So it totally is dependent on the system. The better your system, the faster will be the analysis. Alright, now let's go ahead and check the results. So after we perform the response spectrum analysis, the first thing we need to check if we have attained 90% of mass participation. So for that, we go to the results tab, which is the next tab after the analysis, and then go to the results table. From the results table, we will go to the vibration mode shape table. Alright, so here we go, we see the period of the structure and the frequency of the structure, and over here we can see the mass participation information. Our first mode or our fundamental mode is translation in the y direction. We can say that it's the fundamental mode because we can see that it is like 98.33% of mass participation and 0 in the x, and let's look at the rotational one, which is again 0. So this is 0, this is rotational, this is translation in x, translation in y. Alright, and we just need to look now at the 15th mode shape. That's this one. We need to see if we have achieved 100% of or more than 90% of mass participation. I have reached 100% for x, y as well as for rotation in z direction. So the analysis or the number of mode shapes that I had chosen is good enough. Now we are done with checking one important result. The next important result is to check the base shear of the response spectrum analysis. Okay, so let me just take you through the codes again. Okay. Alright. When either of the methods is used, well, as per clause 7.7.3, whichever method we use, either it's the time history or the response spectrum method, we need to take care that the design base shear, the dynamic design base shear, is not less than the static design base shear. Alright, so in short, we need to compare the dynamic base shear with the static base shear. And so that the dynamic base shear is not less than the static base shear, we need to apply a scale factor. So let's just check if this is smaller than the static. Okay, so for that we will go to the gen program and we will look at the shear force for the response spectrum. So we go to the story tables and story shear and let's look for the RS major and RS ortho. So here we go. We go to the story shear force coefficient table, and here we have the story shear forces. We are going to look at the 1F level, which is our foundation level, and we have over here the result. It's 292.43. Alright, and over here it is 203.32, and let's see now the static base shear by simply right clicking on the static base shear from the work stream menu and going to the seismic load profile here. There we go. This is a story shear column at the ground level. The static base shear is 474.97, which is greater than the dynamic base shear. So of course we are going to be scaling up the dynamic base shear. To scale the dynamic base shear in MIDAS Gen, you have two methods. One method is by going to the pre-processing mode and applying the scale factor in the load cases, response spectrum load cases, or if you do this, then you need to perform the analysis again. The second method, which is recommended, which is very easy, you do not need to perform the analysis of the entire structure again, and that is by going to the load combinations. Alright, so you can go to the load combinations in the results tab, and here we have auto generation of load combination. We can use the steel code, and here we can simply provide the scale up factor for the response spectrum load cases. The scale up factor, well, I had already calculated, however, let me also show it to you. So basically it's going to be 292.43 or something, I don't remember exactly. That's the value. 1 second. We're going to okay, I got that. The values are 474.94 for the static base shear, and that will be divided with the dynamic base shear, which was 292.43. Okay, so we have the value of 1.62 as the scale up factor. So 1.62 is the scale up factor for the major response spectrum, and for the minor, it's going to be 474.94 divided by 203, so that comes to 2.33. We will select orthogonal and 2.33 and click on add, and then click on OK. So as you can see over here, unlike any other software, the program provides us with load combinations as per the standard, along with the scale up factor without performing any analysis, like reperforming the analysis. So we can see over here how the scale factors have been multiplied with the scale up factor for the response spectrum load cases. Also, you can observe over here that the steel strength and serviceability envelopes are automatically generated by the program. So this is a very time-saving feature that's available for you in MIDAS Gen. Yes, we also are going to see what is the major and minor angle. So let's go to the response spectrum load case definition and go to the properties. Alright, so this is the major, and we can see here the excitation angle is 0 degrees. This means the major angle is in the x direction. And if we look at the ortho, then the excitation angle is 90 degrees. So that's the major and minor angle for our structure that have been automatically taken by the program, and thus we do not need to go for the 130 rule. Okay. So that's about the response spectrum results that we can check. Of course, we can go ahead with different result displays in MIDAS Gen program. So let me take you through what all result types you can check in MIDAS Gen program in a very short time. Alright, so one thing is you can get the results in the form of display. So I'm going to be like selecting envelope strength envelope here, and looking at the vertical reaction. So you can see over here the display on your screen itself, and this is the red arrow where the maximum reaction is taking place. This is one thing. Secondly, we can get the result output in the form of tables. Alright, and this table can be exported to Excel sheets. You can also copy and paste few of the results into Excel sheets. Then you can get the results in the form of contour. Alright, and unchecking the values, and also we can get the animated deformation, which can be actually saved in a .avi file format that you can use it for your presentations. Okay, so contour format. Then further we have automatic story tables, like I mentioned earlier in the major strengths, that there are automatic story tables available in MIDAS Gen program. You can get the story drift check, you can get torsional irregularity, that is stiffness irregularity, that is soft story check, and capacity irregularity, that is weak story check, performed by the program automatically. Also, there is a torsional amplification factor that can be given by the program automatically. So as an example, let me just show you the story drift. So when you check the story drift for the dynamic response spectrum loading, here you can simply provide the factors, the scale up factor for our major angle, major response spectrum load, and the allowable ratio of drift was 0.004. Yeah, that's right, and then click on OK. Alright, so here we go. We get a table which gives us a remark automatically if the story drift is within the limits or it is beyond the limits. So it says okay or not good. Okay, this is one way, that is a tabular result. Now using this table, we can also generate graphs. So you can get the story drift ratio, allowable story drift ratio, and the story generated in one graph. So there's a graph for you, and this graph you can take as an image. So this is how intuitive MIDAS program is when it comes to result output. Okay, so we are done over here with the response spectrum procedure as well as checking the results. Now let us go ahead to the next part. Okay, so we're going to be looking at the inelastic time history analysis, which is a non-linear analysis, a non-linear dynamic analysis. Alright, so let me firstly tell you that in MIDAS Gen, it's not just inelastic time history analysis you can perform, but using the time history functions, you can actually go for a linear dynamic analysis, or you can go for non-linear dynamic analysis, or you can also go for non-linear static analysis, which is like a pushover analysis. Alright, so basically we can also like along with the dynamic seismic load, we can also perform the machine vibration analysis. Also we can perform pushover analysis. Also we can perform the footfall analysis. Alright, so let us go ahead now in MIDAS Gen program and get a quick demonstration on performing non-linear dynamic analysis in MIDAS Gen program. Alright, so let's go ahead. It's important for us to understand that time history analysis cannot be performed along with the response spectrum analysis, of course, because time history does include the option to perform the response spectrum analysis itself. So we're going to be deleting the function, response spectrum function, so that the response spectrum loading is removed. And then we'll go to the loads tab, and under the dynamic, we can see over here there is a time history analysis section. Okay, there are many tools that you can see over here in the time history analysis data. Well, it might seem scary, but it's not that so. You don't have to like worry so much. Just have to go through few steps, few procedures that are important. And this time history analysis procedure is actually also mentioned in our online help manual. So if in case you forget anything or you need some help, you can just simply click F or type tab F1 from your keyboard, and then you can see what is the procedure. Okay, so let us see what is the procedure. Okay, so first important part in time history analysis is having a mass. Okay, so mass has been already defined when we were performing response spectrum loading. Second one is the eigenvalue analysis. If you're doing modal analysis, we need the mode shapes by performing eigenvalue analysis. Alright, and that's the thing. And next are just three important further functions we need to do. One is time history function definition, second is the load case definition, and thirdly is ground acceleration. Ground acceleration in case you want to perform dynamic earthquake, or you want to perform footfall analysis or machine vibration analysis. So that's ground acceleration. That would be useful to you. You can also use dynamic nodal loads and time varying static loads for performing the different types of time history analysis. Alright, so options are available for you. Just have to see what is appropriate for the type of analysis you wish to perform for your structure. Okay, so let us start with the procedure. We are done with the first two. The third one is time history function definition. So we click on time history functions, and here again we do have two options. Time force function can be defined, and we can also have a sinusoidal type of function defined. Alright, so we can go over here now to define this time force function. Now in MIDAS Gen program we have an advantage over here. I would like you to just take a quick detailed look. We have 32 earthquakes available built in MIDAS Gen program. So these are the major earthquakes all over the world which you can use to check your structure with. Alright, so this is one thing. Also, you can import your own earthquake functions using the importing function. Alright, so I'm going to be using this L centrosite 180 degrees to apply my loading in the X direction. And as you can see over here, the time force functions have been defined, and these are the values which you can modify it. You can copy paste from Excel sheets as well. It is Excel compatible. Another advantage is that we have heel drop, that is for walking loads, or you can say footfall analysis. So we have different built-in load types available. There is walking and running as well, if you would like to perform such type of analysis in MIDAS Gen program. So all the functions are available, and then further, to finish with the definition, we simply click on OK. Alright, so we are done with the time history function. We'll close this dialog box and go ahead to define the load case. So time history load case is actually one big function that is like the most important function over here, tool over here. Let us firstly name this as a non-linear type of time history. Okay. For that, we are going to be choosing the non-linear type, analysis type. We do have linear as well as non-linear, as I mentioned in the presentation earlier. Alright, so we have non-linear, and then in the non-linear as well, there are three analysis methods available. One is modal, direct integration, and the next is static. Modal and direct integration is for the dynamic, and static is for the static nonlinear analysis, which is like pushover analysis to perform performance-based design. So as for the code, let us see how to perform modal time history analysis. That's why we're going to be using the modal analysis method. Okay. Next is the time history type. Now we do have transient and periodic over here. Transient is used basically when we want to like have a time period completed or time course function completed once, and then there is periodic wherein you want repetition of the time course function until the end time. So these are the two types of time histories that you can utilize. Alright, next is the end time. So this is an iterative procedure, it's a nonlinear analysis, so we need to provide end time and time increments to perform iterations. So here I'm going to be giving 10 seconds and time increment as 0.01 second. It's important to understand that the time increment value that you give over here is good enough so that you obtain accuracy. So the lesser the value, the more accurate your results would be. Okay. I'm keeping 0.01 itself because I want to perform the analysis quickly. Of course, you take more time increments, more time for the analysis. Next is the step number increment for output. So this is basically the number of increments multiplied by the output. So that's 10 again. Alright. Then further we have the option to perform number of time history load cases in sequential order. Like you can firstly define one type of nonlinear analysis, and then you can go ahead perform a linear analysis after that, or maybe first linear then nonlinear, like that, and that can be done in the sequential manner. And you can then check on the subsequent option where you can actually select the load case, the time history load case. Other than the time history load case, you can also use the static load cases that are defined right over here. Alright, we are not having any previous load case, time history load case, so we are not going to be using this part. Alright, in time history analysis, you can perform large displacements as well. Okay, that means large displacement analysis can also be performed along with the time history analysis. Okay, so we're going to be performing this modal time history analysis, and we're also going to be using a damping method. Now in MIDAS Gen program, we have four damping methods available. One is the modal, second is mass and stiffness proportional, and the third is the strain energy proportional. The fourth one is the element mass and stiffness proportional method. Alright, so that is activated when we are going for the other type of analysis. So anyway, so basically we have options over here, different options over here. You can actually get the damping based on the masses separately and stiffness separately using mass stiffness proportional or at once, like both together. And there is strain energy proportional as well, wherein the program will automatically calculate the damping based on the strain energy. So these are the two good options that are available in MIDAS Gen program, which you can make use of. Then there is modal, wherein you can actually specify the percentage of damping for different mode shapes. Okay, so we are going to be, this is like an entire steel structure, simple one, so I'm going to be like using one damping for, that is 5% for all the modes. Alright, and further you can also modify this damping ratio by selecting different modes and damping ratios, applying those damping ratios over here. Alright, so that's done. Next is for the nonlinear analysis, we need to go ahead with the iteration controls. Alright, and here we can see the step size. Okay, step size is like very small over here, so I'm going to be keeping the step size as 0.01. And the maximum iteration, now this maximum iteration is actually a very good feature in MIDAS Gen program, wherein the program is going to be taking care of the accuracy of the structure. Alright, so then there is the convergence criteria. We are going to be taking the displacement norm itself. Basically, with the help of the iterations, the program is going to be also taking care that the iterations are performed enough that the convergence is obtained. Then if you have boundary nonlinear analysis as well, then you can definitely go ahead with these methods that are available in MIDAS Gen program. Alright, with these information, these parameters, we are good to go ahead to finish with our load case definition. Alright, now we are going to go ahead to the next important tool, that is ground acceleration. In the ground acceleration, firstly we select the time history load case name. It's just one that we have defined, so it's available. Then I'm going to be applying this loading in the x direction. So function for direction x selected, and then there is scale factor and arrival time 0 seconds, as in it is immediately going to arrive as we start with the analysis, so that's 0. And then further, the angle of horizontal ground acceleration, this I'm keeping as 0 degrees itself, and after that we can simply click on add. Alright, we are done with defining the time history load cases, the function, and the ground acceleration information. All we need to do now is go ahead and perform the analysis. Before we perform the analysis, I would also like to mention to you that we can define the non-linearity in time history analysis using different and inelastic hinges functions. We can have inelastic material properties, and also there is option for fiber division of sections for beams and columns as well as for walls. So you can make the most of it using MIDAS Gen program. And when it comes to like fiber division of section, you can have your wall over here, and you can apply different inelastic material properties, in which there is also Mander model available, which takes care of the confined and unconfined concrete. So there are many options available for you to explore in MIDAS Gen program. And because of less of time, we're going to go ahead and performing the analysis. Alright, analysis has been performed. It's in 0.75 seconds. Okay, so now let's see where we can get the time history results. So in the results tab, we are going to be looking at the time history section, and in that we can see over here different results like displacement, velocity, acceleration. So here we go, we can look over here with these number of steps that are available. Let's say I'm looking at 5.9 step, and I want to look at the displacement, and I would like to animate, and click on apply and record. Alright, so as you can see over here, this is how the structure is animating because of the earthquake that has been applied on the structure. Okay, so the deformations have been recorded by the program. All I can do is simply save it into an AVI file format. Okay, this is one result that we can get. Next, we can also get the force diagrams for different time steps. Time steps, and we can also move these time steps by just clicking merely over here. Alright, so these are the results that we can get. And have a solid fill as well. We can activate few elements and to check the results of those. Okay, I'm sorry, I'm delaying this webinar a little bit, but I hope you can just put along with me for another 15 minutes. Not 15 minutes, it will be less than that itself. Okay, so that's about the diagrams, time history force diagrams that we can get. Okay, and then let's go ahead and see how time history graphs can be generated by the program. So we have time history graph right over here, which we can simply click on define or modify the function. Okay, so we can select over here what we want to look at, if it's displacement, beam forces, wall forces, and so on. Then we need to click on this add new function and provide a name to the function. So I'll say displacement function. Okay, and I would like to check the displacement of the roof. And that's the displacement. I would like to look at the relative displacement, or there are different other options available. The component I'm looking at or I'm interested in is the dx, since my load has been applied in the x direction itself. Alright, so that's done, and we click on OK. Alright, and we can go to back and then check on the displacement function, add it in my vertical axis, and the horizontal axis will be the time. I can choose otherwise. Okay, so it's time for now, and the time history graph title is going to be displacement itself, and then with respect to time, let's generate the graph. Alright, so here we go. We have got the time history graph for the displacement at different time intervals, and this you can actually save as Excel sheet and check out the displacement graph in the Excel sheet. You would love it. So basically it provides us with this graph and the values as well. Alright, so that's the result for you when it comes to time history analysis. I hope you have not felt boring or not too much of information overload, or I'm sorry if anything has missed. Let's go ahead now back to our presentation and conclude our webinar session by looking at the benefits in MIDAS Gen that we have seen throughout the session. So we have seen that the user-friendly interface has helped us to understand the entire structure, which was already there in front of us. Then we also saw that there is automatic excitation angle for response spectrum analysis. It actually showed us that the 0 or x-axis was the major axis for maximum base shear applying response spectrum loading. Then we also saw that we can add the positive negative signs to the response spectrum results, which has been mentioned by the standard, by Indian standard ISO 190-2016, to be the most critical factor while taking the response spectrum results. When it comes to time history, we have seen that there are 32 types of built-in seismic accelerations which we can make use of. And we can also perform the footfall or floor vibration analysis using time history functions apart from the dynamic seismic analysis. We can perform performance-based design, that is PBD, using time history and pushover analysis. Well, that reminds me to take you through what all loads that we can apply to our structure. Basically, some more advantages include the temperature loads that can be applied, the pre-stressing can be done, then construction stages for long-term effects as well as column shortening analysis can be performed, moving loads for gantry crane girders as well as vehicular loading on ramps can be used, and heat of hydration analysis for mass concreting of structures like foundations, dams can be performed in MIDAS Gen program. So these are the benefits in MIDAS Gen program. When it comes to dynamic analysis, you can look at these ones listed. Alright, so we're going to be ending the session now. Thank you very much for attending. Have a great evening. Bye-bye.